Good afternoon. I'm Jiawei from Nanyang Technological University in Singapore. I'm excited to present switch-GNN, a framework to accelerate GNN training on massive graph. This is joint work with collaborators at Central South, Hong Kong UST, and Tsinghua. I will walk you through the problem and our solutions using programmable switches in data centers. Graph neural networks, or GNNs, are specialized neural networks built to learn from graph-structured data, like networks of people or molecules. GNN can model molecular structure to accelerate drug discovery. Another important use is in pandemic preparedness. Imagine digital contact tracing. People as vertices, their interactions as links. So GNN can predict how fast diseases can spread through these networks. But these graphs are massive, millions of vertices, billions of connections. So training them quickly in data centers is critical for real-world application. GNN work in two main steps. First, each vertex gathers information from its neighbors. This is known as message passing. Then, it updates its own representation using a neural network layer. By repeating this process across several layers, each vertex gradually builds an understanding of its local structure and eventually of the entire graph. This aggregation and transformation process is what we call full graph training. It allows GNN to learn complex patterns that span across the entire graph. As graph gets larger, we need to split them across multiple workers, like GPU servers, for training. But this creates a major challenge. When vertices have neighbors on other workers, they need to send their features over the network. A single vertex data may get copied and sent multiple times to different workers. So this results in one-to-many multicast traffic. Then comes aggregation. Now, many vertices send their data to one place, causing many-to-one contention. This traffic pattern creates a bottleneck. In some data sets like Reddit, each feature can be duplicated up to 16 times. That leads to serious bandwidth contention, sometimes taking up to 80% of the training time. To scale out GNN training, we need faster way to handle this multicasting and aggregation. That's where programmable switch comes in. In recent years, researchers have used programmable switches to speed up machine learning by offloading communication from parameter servers to the network itself. Take NVIDIA's Spectrum X photonic switch. It delivers up to 1.6 terabits per second per port, really fast. We built on similar principles and leverage Intel's Tofino switch to reduce many-to-one communication bottlenecks. Our approach, push multicast and aggregation into the switch. Instead of sending the same data multiple times, a worker sends a vertex data just once. The aggregators in the switch then combine the data and return a single result. Instead of scaling with the square of the number of GPU workers, the traffic now grows linearly, reducing communication. Now, recent work like switch-ML and ATP in USENIX NSDI 2021 shows how in-network aggregation can boost distributed learning. The switch memory is set up as an array of aggregators, gradients with the same key or sequence number from different workers, GPU servers, go to the same aggregator, and each worker sends a batch of gradients, and the switch combines them, matching ones on the fly. The aggregator then sends the result back to the worker, and it is free out for the next task. So using this switch programmability to do the heavy lifting can reduce network traffic and speed up training. This inspired us to apply in-network multicast and aggregation to GNN training. But this begs the question, how does in-network aggregation benefit GNN training? So while in-network aggregation improves training efficiency, it does not account for the actual graph topology, like which vertices are connected in the GNN. To make in-network aggregation effective for GNN training, we need aggregation schemes that align with the graph's connectivity and learning objectives. So we start with a simple idea, a strawman solution. We cut the graph, and each worker sends their boundary vertex features to the switch. The switch then duplicates each feature to multiple aggregators, one for each neighbor. This aggregator collects the features and waits until all required data arrives before combining them using some neural network operations. Once aggregation is done, the result is sent back to the worker, and the aggregator is free for reuse. If no aggregator is available when the new data arrives, the switch simply forwards the data to the worker for local aggregation. This way, each feature is sent to the switch only once, and the worker receives just one aggregated copy, greatly reducing redundancy. But in our experiments with 100 megabytes of switch memory, we observed some problems. With this naive strawman approach, we simulated a star topology with 128 workers in NS3 and tested both unlimited and 100 megabyte memory setups. In part A, you can see the throughput drops under memory constraints. In part B, aggregator is high, but still much lower than the case with unlimited memory. And in part C, we see long queue length at the switch. And this happens even with more memory. So that's somewhat counterintuitive. And in part D, the overall traffic volume remains high. So the switch is not offloading much. So with limited switch memory, the strawman solution does not scale very well. So why does this strawman solution perform poorly? The main problem is the random sending orders. The switch ends up waiting for data from all neighbors before it can aggregate. This causes delays. Look at the figure. At time 0, some features arrive early but just sit there waiting for others. The switch output stays idle. Only when the missing neighbor shows up at time 1, multiple aggregators finish simultaneously and overload the output port. The second issue is that interdependent vertex features cause aggregators overflow. Each vertex needs as many aggregators as it has neighbors, and those neighbors depend on their own neighbors. So this forms large connected groups, and this group demand more aggregators than the switch can handle. For example, as shown in the figure on the slide, 3 connected red vertices need 10 aggregators, but the switch only has 4. So 6 features get sent directly to workers, missing the chance for in-network aggregation. So the strawman solution ignores the graph structure and their dependencies. So we need a better approach to fix these issues. That's where switch GNN comes in. It is built to make large-scale GNN training far more efficient. Leveraging programmable switches, switch GNN is built around 2 key ideas. First, we reorder how graph data is sent across the network. This graph-aware multicast reordering helps optimize data flow and reduce delays. Second, we use multi-level graph partitioning to break down the graph structure, to manage memory better and prevent overload. To keep things running smoothly, we develop congestion control mechanisms that run on programmable switches to make sure data is aggregated correctly and the network does not get congested during heavy communication. First, for graph-aware multicast reordering, we reorder how vertices are sent. We prioritize the transmission of high out-degree vertex features. This illustration flips what we saw earlier. Now we send vertices with high out degree first instead of random assignment. This keeps the throughput pipeline efficient. To identify high connection vertices, we use a priority-based breadth-first search approach. Starting from a chosen vertex, we queue its neighbors based on how many connections they have, and the more outgoing connections, the higher the priority. The final order in which vertices are sent or dequeued then determines the order we send to the workers. For example, in the Reddit graph dataset, just 20% of vertices hold 80% of the connection. That's Pareto's principle. And if topologically close vertices arrive at the aggregator at the same time, one after another, it can process them quickly and free up resources faster. That's why it is important to identify GNN features close together in time. Now, let's look at the aggregator memory challenge. Boundary vertices tend to form large connected clusters, like the one shown on the slide, and these clusters require more aggregator memories than what the switches have available. So we first break the boundary dependencies by partitioning the graph into memory-sized blocks and transmit them in batches. We use a graph partitioning tool called Metis to break large clusters into smaller blocks, block 1, block 2, block 3, and so on, that fit inside the switch memory to avoid overflow. Now, splitting creates cut edges between blocks, so we have to send data for these edges to keep graph propagation accurate, trading off a bit of extra traffic for correctness in training. We can use more advanced graph partitioning algorithms to minimize the number of cut edges. Now, this process repeats iteratively until all the subgraphs can fit within the switch memory. To track the vertex to aggregator mapping between the GPU workers and the switches, we use bit maps. One tracks which vertex data has been sent, and another monitors data received from neighbors. When an aggregator finishes processing and produces a result, it sends acknowledgement back to the neighbors. We also develop a congestion control mechanism inspired by DCQ-CN, or Data Center Quantized Congestion Notification Protocol, to manage congestion. It uses DCN mux to detect congestion early and adjust the sending rates dynamically so that in-network aggregation are robust even under heavy traffic conditions. Switch GNN runs on Intel P4 programmable switches, and for cross-rack communication, we use fast local links like NVLink between GPUs. Our testbed has 8 machines connected in a star topology. We train the GNN using OGBN products, Yelp, and Reddit datasets, and compare with benchmarks like BNS-GCN and GraphCube. Look at Figure 1 for throughput on OGBN products. Yelp and Reddit, switch GNN was 54% faster than BNS-GCN and 24% faster than GraphCube. Figure 2 shows that GPU servers work harder under switch GNN because network delays drop for switch GNN, which has faster convergence time. Figure 3 shows that graph partitioning iterative algorithm still gives correct results. We also ran large-scale tests using NS3 simulations. We allowed switch memory to go from 10 to 100 megabytes, realistic for today's switches, and we measure epic time, traffic volume, queue length, and aggregation speed. Switch GNN can reduce epic time significantly. On the Reddit dataset, it was 74% faster than BNS-GCN and 83% faster than the naive strawman solution. Switch GNN can reduce the traffic volume by up to 81% compared with existing full graph training solutions with 100 megabytes of switch memory. Even with 10 megabytes, we can save 23%. You can find more evaluation results and details in the paper. In summary, switch GNN uses programmable switches to accelerate GNN training by up to 74% in our experiments. Leveraging graph structure and in-network aggregation can increase training efficiency and quadruple throughputs in the data center. The key takeaway is that the unique characteristics of GNN workload can and should be exploited to jointly optimize data center resources and learning performance. I'm looking forward to discussing this further with those interested. Thank you.